Okay, everyone. I did send out an email that you know, wasn't real happy with the way the class flowed last time, so I redid the video of the class, basically, going through the notes, posted on YouTube. The video I did in class, I'm not going to post it, just chunked it. So if you were confused last class, you want to go back and watch it, it's cleaned up a little bit. Now, if you tried the homework, then you will have probably run into some issues because the homework doesn't seem like it's connected at all to what we did in class, but it is. So I wanted to, before we start chapter 13 today, I wanted to run through a couple of problems out of the homework just so we can see how these problems can be done based on what we did last class. So I'm looking at 12.8, number 11, if you have the book. It basically tells you that you have a region that's bounded by the four curves given up here, all right? And it wants you to find a transformation, find one. You create your own that will take this region S and transform it into the UV plane. So this is the XY plane. Transform it into the UV plane, where the sides of the transformation are parallel to the U and V axes. All that's saying is try and get this to look like a rectangle in the UV plane. So the way we do this, first what I did is I took each of these equations. They're all lines, and I graphed them. Does it seem brighter in here today? I don't know what's going on. I'm afraid to do that. That's a little too dark. Maybe because it's just really small. Maybe I'll zoom in on that a little bit. Okay, so take all these lines and I graph them. They're color-coded. The black one is here, the red one, green and blue, right? So if you look at this, it looks kind of like a parallelogram, right? We have to come up with the transformation. We have to come up with the U equals and V equals. And this is what they're going to be, but I want to explain why it is that they turn out this way. What we want is for one of these, let's just look at S1, which is this line right here, this side. I want S1 to go from a line, right, a line that has some slope to it, to become one of the sides of a rectangle. On one of the sides of a rectangle, one of the variables is constant, isn't it? So like if I look at this one, S1, because this is what's going to happen to it. S1 here, my U is constant, isn't it? If I'm in the UV plane, the U is constant, the V varies up and down. So is there a way to create a transformation that takes a line down to create the U variable being constant? And then also doing the same thing for each one of these. I want each one of these to turn the line into a constant in the UV plane. Kind of makes sense? So what I do is I take these two lines that are parallel to each other and I solve them, or I basically move all the variables to one side. So if you take y equals 2x plus 1, take all the variables to the left side, you get 2x minus y equals negative 1, right? If you solve the other line, or move all the variables over to one side again, you get the same exact thing. Look at this, 2x minus y again. And that's the key. We see 2x minus y appear twice. And in one problem, it's equal to negative 1. In the other one, it's equal to positive 1. So if I call this blue part, which is identical, if I call that u, then u will be equal to negative 1 and u will be equal to 1, won't it? It'll be equal to constants. So that's why there is the choice of u equals 2x minus y. It's out of convenience. And the problem had to be made very specially so that this would work. All right, so keep that in mind too. Now, if I look at the other two lines that are parallel, these two, that's these two equations right here. If I move all the variables over on both of those, look what happens. I get x plus y equals 3, and I get x plus y equals 1. Again, they're identical. You have x plus y, in one of them it's equal to 3 and the other one's equal to 1. So again, equal to constants, aren't they? So if I call v the x plus y, then I'll have v is equal to 3 and v is equal to 1. That kind of makes sense? Okay, so let's choose those transformations. U is equal to 2x minus y, v is equal to x plus y, and then I go on to say what happens on S1. So on S1, we're right here. On S1, 2x minus y equals 1. So that means 2x minus y equals 1. But wait a minute, 2x minus y is u. So u is equal to 1. Therefore, the image over here is the image of S1 down through this transformation is u equals 1, which is this line. Notice what I did not do is try and figure out what's happening with v. I said, look, if I'm on S1, u is 1, so u is constant. The v, well, it can vary up and down. So I just drew a vertical line. I didn't stop it anywhere. So imagine you just have this line right here drawn, goes up forever, down forever, all right? Well, let's just leave it like that. Then we come in and we say, what happens on S2? Well, S2 is this line right here. If we move things around, that's x plus y equals 3. But again, x plus y was v, so that means v is 3. So the image of S2 through this transformation is v is constant at 3. So here's the uv right here. Here's the origin. Go up 1, 2, 3. We're across there, right? V is 3. And again, I don't care what's happening with u. I'm just going to let that line go in each direction forever. Then I do the same thing for S3. On S3, I get 2x minus y is negative 1, but 2x minus y is u, so u is negative 1. So that gives me this line. And again, it goes up and down forever. And then finally, S4, you do the same thing, and it'll say v. It'll turn out to be that v is 1. So you get those 4 lines, and they enclose a new region, and that's a rectangular region, isn't it? So we're done. Yes? Yes. Good question. I chose my u to be 2x minus y and my v to be x plus y. If we would have done it the other way around and said v is 2x minus y and u is x plus y, our picture would have changed a little bit, but the integral still would have been the same. It's rectangular, and the Jacobian determinant would be a little different, but everything would work itself out. It would be the same. We could do it. You could show it both ways and show that it turns out to be the same. Now, is it asking? It's not asking in number 11 for you to actually do anything else. Just what are the transformations? These are not unique transformations. All right? These were the transformations, right, that were chosen? They are not unique, meaning that there was other ways you could have created rectangles out of different transformations. Like you said, you could switch the variables. So there's more than just one answer for this. Also, and what I did here is I took the equation for u, the equation for v, solved the first equation over here for y, so move things around, plug that y into this equation, solve that for x, and then what I do is I get an equation for x in terms of u and v, and over here I get an equation for y in terms of u and v. Why would I want to do that when I'm doing these transformations? Why would I want to get x in terms of u and v and y in terms of u and v? For the Jacobian determinant that I would need later if I was going to do the integral, the double integral, right? Because the Jacobian determinant requires the partial of x with respect to u, partial of x with respect to v, partial of y with respect to x, y with respect to u, y with respect to v. So you need all those partials. So you've got to get it in terms of x and y. So if you had not done your homework, you're probably looking at this going, oh, okay. If you had tried it, then hopefully this helps a little bit on where things were going. Now, number 13 is, where's 13? Same thing. They do not give you what the transformation is, but they give you, it's the region bounded by these two curves in the first quadrant. So, this is a circle radius 1, this is a circle radius 2. First quadrant means we have this little portion. It looks like a polar region, doesn't it? And that's exactly the substitution we should make, right? Polar coordinates. That's what allows us to look at things like this and turn them into nice rectangles. So you had to kind of make the connection here that polar came from this whole concept right here. So we make the connection. We say x is then equal to, we had used r cosine theta, but we'll use u cosine v just to keep our variables, consistent. Then the y is u sine v. If you do that, then look at what this first equation becomes. X squared plus y squared equals 1 is the same as all that polar conversion, which means u squared is 1, which means u is plus or minus 1. Y'all agree with that? This right here was Pythagorean identity there, right? Factor out the u squared. And then it looks like I say u is equal to plus or minus 1, and then I say u is equal to 1. Why do I say u is only equal to 1? It was first quadrant, right? First quadrant. But that was up here, first quadrant. So why only 1 here, not -1? Think about it. We'll think about it while we continue this, okay? I'm going to keep working, but there's a reason why we're not looking at the -1 here. What about the other circle? X squared plus y squared equals 2. If I rewrite that equation, that basically turns into u squared equals 2, and that means that u equals plus or minus root 2, right? Yes? But u is only going to be positive. Again, why is it only positive? Well, we'll talk about that. But here it is. Here's what u being held constant turns out to be. Y'all with me on that or not? Okay, so all that gave us, all that was, I didn't label things S1, S2 here, but all that was the inner arc and the outer arc. Whoa. That's all we just did. That inner one and that outer one correspond to those two vertical lines. What do we still need? What do I need to consider? Yeah, I did this part right here. I did this part right here, but I need to still consider that part right there and that part right there, those two pieces. So let's look at this one right here. That little line segment, right? What can you tell me about that line segment? X has to be 0 on that line segment. So if I say X is 0, and you don't even need this Y restriction. If X is 0, X, I wrote this real small because I was just going through the problem real quick. X is the polar conversion. X is r cosine theta. For us, it's u cosine v, right? So if X is 0, then that means u cosine v is 0, right? That means that u is 0 or cosine of v is 0. So just take each of those factors, set them equal to 0, right? What if u is 0? If u is 0, wouldn't x and y be 0? Right? And then I couldn't be up here, could I? Right? So that can't happen. That means cosine of v has to be 0. And if you take, r cosine, or if you think about it, where's cosine 0? It's at where? Pi over 2. So v must be pi over 2. So basically what we're saying is that little piece right there forces our v to be constant at pi over 2, which is why up here my v is constant at pi over 2. This line right here is the image of that left side up there. Now what about this piece right here? What can you tell me about that piece? Y is 0, right? This is not it. It comes down this way. If y is 0, then the same thing happens. That means u sine v, because y is the y coordinate, right? We use sine. U sine v is 0, which means what? Again, you don't have to worry about u being 0, but sine v is 0. Where is sine function 0? At 0. And pi, but remember, we're restricting ourselves. Remember the restrictions up here? What was the restriction on our angle? 0 to pi over 2. So That means that V would have to be 0, which is this line right here. So what you get is the region in here, like that. Okay? I hope that makes some sense. Let's see, did I do more? Number 19. These were a little more complicated. They gave you the double integral. They wanted you to look at this region bounded by these 3 curves. Y equals x, identity, right? Y equals 3x, identity, slope 3, basically. Y equals, xy equals 1 is the same as y equals 1 over x. So that's this one right here. And then xy equals 3 is the same as y equals 3 over x, which is this one right here. And then here are your 2 lines. So you can see that region. They give us the transformation in this problem. X is u over v, y is v. So you can start solving. Let's see, if you take, how do I get this? Vx equals u. Just multiply this one by v on both sides. And then, what do I do here? Substitute, right? Look, v is what? V is x, or v is y, so that becomes a y. So u is xy. And then, well, v is y. Well, that means v is y. So this is my transformation, okay? This is my transformation where x is in terms of u and v. Here's me switching it. Transformation is now u is in terms of x and y, and v is in terms of x and y. And then what you can do is you can start going through each of these. It's pretty straightforward. I'll just do 2 of them. On S1, y is x, right? What happens to that through this transformation? Well, S1 is y equals x, so I just write that down, y equals x. But what was y? Or what was x? How do you want to do this? I got to scroll this up a little bit. How did I get this? How did I get u equals x squared? Look at this equation. Look at this right here, right? U is xy, right? But what's y? Y is x. So u is x squared. What is v? Well, v is y, isn't it? So v is x. I know, it is like what the egg or the chicken here. What happened first? So u must be x squared and v must be x. That means that u must be v squared, right? If v is x, then that's v squared, so u is v squared. That means v is the square root of u. So this is all just algebra, right? To try and manipulate. What I'm trying to do is get my head around what the hell this line looks like as I transform it. And what happens is you get basically a square root function. So you get this right here, this square root function. And then if you do the same thing on the other one, which is the other green line up there, you get another square root function. And if you take the 2 curves in here and map those over, you get constants. All the work is in here. I'll send this out later so you can look at it. All the different work of what I did to get to these things. And then you look at this region and you say this is a type 1 region, right? You have some function on top, some function on bottom. Your u is trapped between 1 and 3. You get your Jacobian determinant, which turns out to be 1 over v. And then here's what your double integral transforms to be. Integral from 1 to 3, root u to root 3u, that's those 2. And then u over v dv du. I'll leave it to you because it was homework, but I just wanted to help you kind of guide a little bit on how this worked out. If we weren't given what restrictions? This one is not so clear. No. Yeah, this one is not so clear where the restriction, or where, the question is, how would we know to make u, x, y, and v, y? From, This right here? Yes. It's all about this one, right? So yeah, these two are identical. XY equals 1 and 3. So it makes sense to make XY one of our transformations, because that would be like U is a constant, U is a constant. Now, that's what happened here. Y over X is equal to V, right? If you do Y divided by X here, Y divided by X, then you'll have it's equal to 1 and 3. So yes, you could. Now, it turns out it doesn't go quite as cleanly. As we can see, it didn't go to a rectangle, but still. That would be at least a place to start mentally. You know, where do we begin to even try and come up with them? Okay, I hope that clarifies, you know, some of the stuff from the homework. I think there's one more I'm not going to go through, but it's the same exact logic behind it. They give you, yes, they give you the transformation. Yeah, that one is very obvious, right? Is that obvious to everyone? Right? XY is one of the transformations. XY squared is the other one. Or XY is either U or V, and the other one is either U or V. You pick. All right. Thank you for letting me go through that. I felt like I needed to spend a little bit of time on that today before we begin chapter 13. So everyone should have a copy of the notes. If there's any mistakes on the notes as far as they're not bound properly, it's not my fault, no. If your binding's falling apart, it's because I went to slave labor to put these together today. Is yours backwards? Here you go. Well, I tell you what, I've got an extra one up here. I have an extra one. Do you want one that's... Well, let's see, maybe. And one of them might have writing in it, because one of them used to be mine. I was scribbling around on it. Okay, so this is obviously chapter 13. This is the last chapter in the book. The only thing that it's lacking is whoa, this has got all messed up. 13.9 is not in here, but I will you know, add it later on. I'm sorry, I just didn't have it ready to go today. Now, this is a summary of all of the formulas from chapter 13. Chapter 13 only. So there's a lot of information here as far as formulas are concerned. So this is a nice little thing. Keep it handy. You'll be able to use that on your final. You won't have to write anything. You'll just be able to walk in with that packet. I did, but I'll forget when I need to do it again. Yeah. All right, let's start chapter 13. This is an exciting time now. Not yet. Because this first section is kind of boring to me, but I'm excited for you all. I think the first section is pretty easy. Yeah. There's no magic. There's no crazy formulas. It's just some concepts. So vector fields. All right, vector fields. That's where we're starting. So we have the definition of a vector field in two-dimensional space. Let D be a set in the plane. So a set, like we've had regions in the plane, let D be some set in the plane. A vector field on D is a vector function. So that's a capital F with that old vector symbol over it, right? That assigns to each point xy in the two-dimensional space a vector. So every point in the plane or every point in that region has assigned to it a vector. Here is your first example. And what I'd like to do is I'd like to sketch this separately, and then we'll come back to it, all right? So let me get this capital F of xy equals, was it y negative x? Negative yx. Bus. All right, so here's what I'll start with. I'm going to start with just a picture of two-dimensional space. And I'm going to pick a point in that space. So let's pick the point 0, 0. Right? That's the origin. And let's plug 0, 0 into this vector function. So I'm plugging in 0, 0. And what is it spitting out? 0, 0. But it's a vector, isn't it? And the 0 vector is just basically a dot. I mean, it's nothing. Right? It has no length, has no direction. So that means that at the origin, corresponding to the origin is a vector, and that vector is the 0 vector. So let's move somewhere else. Let's go out the x-axis. Let's just go take a look at f. Let's plug in the point 1, 0. What does that function, vector function, spit out? 0, 1, right? 0, 1. So if I go out 1 unit to the right, so there's 1, corresponding to that point, which I'll put in black, is a vector, right? And this vector is the vector 0, 1. What does the vector 0, 1 look like? It points straight up. How long is it? It's 1 unit length, right? Isn't that J? J hat? Y'all buy this? Y'all understand this? So at that point, there's a vector. Now let's go out one more. Let's go to f of 2, 0. What's happening there? We get a vector 0, 2. So that means at the point 2, 0, which is out there, I have a vector that points straight up again, but how long is it? It's 2, so it has a length of 2. Well, it's the square root of, it's the square, remember you square each and then you take square root, so it would be 2. And then what would the next one be? If I went out to 3, 0, it'd be up, but 3, wouldn't it? You follow? Now, what if we go the other direction on the x-axis? What if I go negative 1? How does that change things? What is f of negative 1, 0? 0, negative 1, right? So which way is that pointing? Down 1? If I go out to negative 2, what do I got? Down 2, like that. Negative 3, down 3, right? You understand the basic concept here? At every point, there is a vector. How about going y-axis? Let's go up a little bit. What would f of 0, 1 give us? Negative 1, 0, right? Which way is that pointing? To the left 1? So at 0, 1, which is up on the y-axis, I point to the left 1, don't I? Like that? What if I go up to 0, 2? What's going to happen? It's going to point to the left 2. If I went up again, left 3, right? What about if I go negative 1? So I come down 1. You can plug it in, you go to the right 1, wouldn't you? And then down 2, you go to the right 2. Right, 3. Now, all I've done is pick points on the x-axis and y-axis, right? But there should be a vector at every single point in this plane. So let's pick something a little more interesting. Let's pick maybe the point 1. Let me go 1, 2 since it won't be covered up. How about that point 1, 2? If I go to the point 1, 2, it's going to point, the vector that I get out is negative 2, 1, right? Negative 2, 1 from here means what? To the left 2, and then up 1? Left 2, up 1 would be here. I'll put it in red so you can see it. It's pointing like this, right? There looks like, I mean, just from the vectors we've put here, it looks like there's almost like this rotational field to this, isn't there? What we want to look at a vector field like, at least in 2D, is imagine you're just a person or an ant or something crawling around on a piece of paper, and maybe there's wind blowing, right? The vector field is basically at every point there's some force acting on you. And so this particular vector field would say that, look, if you're at the origin, nothing is happening, right? I start walking out the x-axis, let's say that's the x-axis, I start walking out, and there's like wind wanting to blow me to the left, right? So it's wanting to blow me this way. I'm walking out this way. The further I go this direction, what? The stronger that vector field is. Got it? Now, what happens if I start walking out and I actually do start to get pushed that way? What's going to happen? It appears that up here somewhere it's going to want to push me this way, right? So it's got this sort of rotational thing that looks like it's happening. Okay? Now, computers can do a much better job of doing this. Now, I can have the computer do the vector for me at any point, like this, move it around. Much better than doing it by hand, right? Or I can just have it do a coarse vector field where it just picks a bunch of random points and shows me vectors at random points. Or it can make it a real fine picture of it. So you got a bunch of little vectors. I think with this, though, you can really see that sort of rotation happening in this vector field. Yeah. Yeah, the arrows, the direction and the length of these arrows mean something, right? This means that the further you get away from the origin, the stronger that field is, or the more force there is. Sure. For this, yeah, the eye in the eye is like nothing happening the further you get out. Okay, that's an example of a very simple vector field. All right. Now, I have a program here that I made that I can just put in whatever vector field you want. So let's make one up. What do you want it to do? You want ln x? That's what. So when I plug in x, you want me to do ln of that? Okay. Of x? How about x plus y? We'll make it a little more interesting. And then how about for the next one, we'll just say it's x times y. No telling what's going to happen here. Yeah. There we go. I had to make it where it was defined. Sorry, it's a limitation of the code I wrote. So let's see what happens as I start to move around here. Oh. You see my vector? Let me take off. I'm going to take off the vector field there. Boy, you see the vector? So as I move out that direction, it's wanting to continue to push me that way, right? But as I move up and down, look, it's trying to push me out. As I move closer to here, it's trying to push me back in towards this. So there's lots of weird stuff happening here. If we look at the vector field, you can kind of get a feel for what's happening that way. Yeah, it's almost, yeah, that's why these are so great, vector fields like magnetic fields. So along this axis, nothing was happening. It's trying to push me out. As I moved away, it tries to start to push me out this way faster and faster, right? But if I come this way, it's trying to push me back in. You got to wake up, man. You're this close to going home, all right? Go do jumping jacks in the hall and come back or something. All right, so that I only put that code in there because some students in the past have been downloading the CDF player and getting these files from me, and they can go play with it themselves. But okay, so now if you have a vector field in R2, well then of course you can have a vector field in R3, which means at every point in three-dimensional space, there is a three-dimensional vector. Now this is more like real life, right? We stand here, you have gravitational force, right, acting on us, pointing somewhere towards the center of mass of the Earth. And that could be considered a vector. The wind outside, right? Everything. The currents within the ocean. Different points in the ocean, underwater currents, changes in temperatures, right? All of that sort of stuff. So it's just, you know, here's an example of a vector function in 3D. So for every point, look what happens. If I plug in an x, y, z, the vector that comes out, the vector field that I've defined here, is the negative y, the x, and the 2z. So I'm going to move around here, and you can see the vector in three-dimensional space. You see it? So every point there is some vector. Now it gets kind of hard to see where we are, right? And if I put in the vector field, it will become a nightmare because you can't really get a good idea of what's happening there, right? And then if I put in more vectors, it just starts to look like a total cluster. Yeah, the computer's thinking about it right now. Yeah. There, right? So now you've got a three-dimensional vector field of, you know, different points. Ooh, I shouldn't have tried rotating that. You can kind of see it. Almost looks like, you know, those big old clusters of birds that'll fly around together and stuff. You know, they all kind of follow. They have their own vector field. They all, you know, wherever the group goes, they all kind of go. Same thing kind of happening here. Okay, so let's just have an appreciation for the fact that we do have a concept of what a three-dimensional vector field is. Yeah. Look at this one right here. This looks like a crazy vector field, doesn't it? Look what it is though. This is really weird. If I plug in x, right? If I plug in x, what am I doing? I'm taking that x, I'm making it negative, and then I'm dividing by what? The magnitude or length of what's x squared plus y squared plus z squared square root. It's the length of the line segment that goes from the origin to that point, right? So I'm picking some point out in space. And I'm saying, okay, the vector at that point, the x-coordinate, is going to be whatever the x value is, negative, divided by its length. And then I do the same thing for the y, the same thing for the z. So I'm pointed out, right? I'm pointed out, like let's say I'm at the origin, I'm pointing to some point x, y, z. The vector coming out of that is pointing back at me, but has been divided by its own length. So it's a unit vector coming back at me. Let me show you what it looks like. You know what? Let me show you the vector first. There it is. I want you to see what it's doing. See what it's doing? It's pointing to the origin. That vector field is a very good example of what? Gravity. In fact, that is the template for all gravitational force vector fields, that right there. What's the center? Yeah, I mean, that's a different question. The center, where's the center? That's different. But you can get pretty close to what's happening in reality using this vector field. Sure. Sure. Okay, you get the idea here? What's wrong? Oh, because the one that I probably put in there, I let the computer decide what it wanted to use. Is that what is on yours? No, no. It's just, this just allows me the option of having more or less so you can see them. Or if I do the fine one, I think it's just going to look like a big blue blob. Yeah. Yeah. So I say here, sketch the vector field, right? You cannot sketch a vector field in three-dimensional space easily. You could pick a few points, draw the vector there, right? But we already know drawing vectors in 3D is hard enough. More of what I wanted you to see is that if we could sketch that and get a lot of vectors, we could really see how that works like gravity toward its center seeking, right? It wants to go to the center. All right, now we talk, this is where we start getting the interesting stuff. Gradient vector fields. Remember, a vector field is a vector function, right? Capital F, we just said a vector field I wasn't sure if I started my mic or not, but I did, thank goodness. A vector field is either this or in 3D this, right? And then we define what these are. But it's a vector function. It takes on 2 variables here, spits out something, or 3 here. That's different. A vector function is different than a scalar function. A scalar function is like f of x, y equals, that's those surfaces we've been messing with, right? Those were surfaces, those weren't vector functions. But remember that with every function of 2 variables, scalar function, we define this thing called the gradient. And the gradient was a vector, right? And it was the vector created by the partial derivatives. Well, that gradient, right, could be considered then a vector function, because it is, right? It's a function, it is vectors, so we can consider it a vector function. So if we take that, if we take a scalar function, we take its gradient, right, in either 2 or 3-dimensional space, then we call that the gradient vector field. It's the vector field generated by taking the gradient of the function. And this is an example where you can see the connection between a scalar function and its gradient vector field. So first, let's take this function, f of x, y, and let's just find the gradient vector field real quick. This is nothing new, right? I mean, like, we've done this enough. It's so much, it's probably relatively easy, so I'm just going to do it over here. I'm not even going to write it down on our notes. What's the partial of f with respect to x? Okay, so the gradient of f, that's the way we wrote it, was the gradient was the partial of f with respect to x, partial of f with respect to y. That's what it was, right? So partial of f with respect to x was 2xy. And the partial of f with respect to y is what? X squared minus 3y squared. This is called the gradient vector field. Yes? Now, if we look at this right here is the surface. That's the f function, right? That's the f function. We know it's like some sheet, you know, waving out into the wind, right? And just boom, there it is, right? So that's just the function. If we look at it from the top, right? We look at it from the top, then we could look at what we call the level curves, where we slice it, we slice it, we slice it, and we try and figure out where we slice it, what it looks like. These are the level curves. So if we're looking at that from the top, here are the level curves. Do you kind of see that these curves up here are where these sides dip down? And then this side over here is where the sides come up. You all see that or not? Okay, now let me add, when we look from the top like this, that's kind of like the domain, right? That's two-dimensional space. If I add the gradient vector field on top of this, and let me make it coarse so you can see it, you'll see that the gradient vector field is actually corresponding to the surface in some way here, right? The gradients right here and right here. Do you remember what the gradient represented? The gradient was the max rate of change, right? So what it's saying is that if we're standing somewhere on the surface and we go in this direction, that will take us to the steepest ascent, which would be like if we're standing here, we want to go steepest ascent, we go kind of towards that middle. So it's saying go towards the middle because that will take you up fastest. So there's like a visual connection between the gradient vector field and the surface itself. Hope that makes sense. Yeah, pretty much. Okay, conservative vector fields. This is important later. We need to define it now. A vector field F, capital F, is called a conservative vector field if there is some scalar function little f such that the vector field is the gradient of F. Students always have trouble with this. I don't know why, but they do, so let me just make sure you understand what this means. This just means the vector function is the gradient, the vector function is the gradient vector field of some function f. What? Look at, let me go back to this right here. We start off, this is a vector field, right? The question now, is it a conservative vector field? The only way to know if that's a conservative vector field is if we can come up with a little f. We have to figure out what little f we could take the gradient of to get that. If there is a little f that I take the gradient of it and get that, then it's called a conservative vector field. It is not guaranteed, though, that that little f exists. And that's the challenge, is to try and determine what little f it came from. Let me go back to this. So I would like to do an example here. And I think I've got the page number wrong here. All my page numbers are all whacked. This is actually page 760 is where this starts. 21 through 24. I wonder if it would be too much. I'm tempted to see if let's try this. I wasn't planning on this, but I think it's worth us doing. Let's take a look. All the homework you can do with everything we've talked about. Okay, the first two are just get some vector fields or something. It's just draw a couple of vectors and do your best. 21 through 24 is basically this: gradient, gradient, gradient. There's no real work here. So what I'd like to do to get us motivated and where we're headed kind of a little bit here is take a look at this. Not that. All right. Remember this? We just had this example. It was x squared y minus y cubed. And we said that if we define capital F to be equal to the gradient of f, we said that that turned out to be 2xy, right? This is what I did over here, x squared minus 3y squared, right? Right? Okay, now, act like that didn't happen, all right? Act like that didn't happen. And I want you to sit here, and I'm going to start with this. F of xy equals 2xy x squared minus 3y squared. Okay, that is an example of a vector field, correct? Is it conservative? Why? Because it came from that? Wait, I told you to forget that just happened. The question is, how do we go back up to this, right? How do we show we can get this from that? So here's the way we do it. So is this conservative? Is F conservative? Yes, but let's see what happens. We have to be a little careful here. Let's take a look at this first one here. We know right now that the partial, if this works, right, if there is a little f, then the partial of f with respect to x must equal 2xy, correct? Let's start right there. Now, what I can tell you right now is the antiderivative of that with respect to x, right? So if I integrate this with respect to x, that's the important thing there, with respect to x, what's the left side got to become? What's the? It's the f function, isn't it? It's the f function. No, because look, it was the whole function, right? See, there's no components here. Well, let's see. Do you follow though that this symbol meant partial of f with respect to x, so the antiderivative with respect to x should take us back to the original function, f of xy. Now the right side, when I integrate this with respect to x, it's what? X squared y plus a constant, but it's more than just a constant, because anything that was a y was a constant to us, wasn't it, when we did this partial? So we no longer say constant. Here's what we say. It could be any function of y. Do you agree with that? So look at this again, and just think back now and say, look, if I started with this, and I said take the derivative of this with respect to x, which means do this first part of the gradient, then you would say 2xy, right? And this would be a function of y only, and you're treating y's like constants, so the derivative of this would be what? 0. With me? Okay. Now, check this out. This is pretty cool. Now, I would like for you to take this result right here, and I'd like for you to start with that, and I'd like to take this and take the partial derivative with respect to y. Don't even worry about this anymore. I'm not telling you to look at this right now. I'm saying work with what we've got here. What is the partial of that with respect to y? Well, what is it? What's the derivative of this with respect to y? X squared y? You get x squared, right? Plus what? The derivative of g, which you don't know what that is, so call it g prime y. You see it? But what do we know that has to be? This up here, right? Doesn't it have to match this? So this, therefore, x squared plus g prime y must equal what we had up there, which was x squared minus 3y squared. You see what I'm doing? I'm matching this up to up here. And then don't the x squareds cancel from both sides? Which means g prime y equals negative 3y squared, which means I can now do what? Integrate again with respect to y, can't I? So if I now integrate with respect to y, I'll put dy out here. What's the left side? G of y. And then the right side, negative y cubed plus some constant, right? Plus some constant. Now, could it be that it has an x in it? No, because remember over here, we said that g of y had only y's in it, right? Didn't have x's in it. Because if it would have had x's in it, then the derivative of it wouldn't have been 0. So now what I do is I come back to this part, and I rewrite it. F of xy equals x squared y plus g of y, which we just said is what? Minus y cubed plus a constant. And what was my function? It was x squared y minus y cubed and nothing else. But this actually gives me the entire family of functions it could come from. So is this a conservative vector field? Yes. What's that? Using which other one? You mean starting right here with y? Yes, you could have done it that way also. Sometimes I think one will be easier. Here's where the challenge is really going to come in. What if this is a three-dimensional vector field? So you have x, y, z now in there. You're going to have to do this process twice. Think about it. If this was just the partial with respect to x, right here when we integrate with respect to x, not only will we have this, we'll have what? G of yz. G of yz. And then you'll have to integrate again. It's going to be a little more work, as we'll see, okay? We are a little ahead of where, this right here is a thought that's a little bit ahead of where we're supposed to be on this, because we're just trying to look at vector fields right now. But they define conservative, so I want you to at least see how we're going to have to work through to convince ourselves something is a conservative vector field. Yep, we're doing good. Okay, so there's homework. Make sure you do it. That shouldn't take you, but I mean, seriously, 15 minutes, the most. It's just a couple of gradients and a couple of drawings. It's not a whole lot more. 13.2 is what I was really hoping to get to, and that's where we will continue now. Line integrals, or curve integrals. Line integrals is not a good name for what these are, as you'll see. So some people call them curve integrals, but most books say line integrals. All right, so just keep that in mind. When you're sitting there going, why do they call it a line integral? It is a bad name for this, all right? So here's where we begin. Suppose we have a function, f of xy, defined on a curve C in R2. And I should say before I move ahead, vector fields are on hold right now. They will come in next class. Everything I'm going to do right now has nothing to do with the vector field, but in the middle of this section, we will start using vector fields. So I'm only going to do half this section today. So let's say we have a function f of xy defined on a curve. F of xy is a surface, right? Surface. There's my surface, three-dimensional surface sitting out there, right? I'm defining it on a curve, which means I'm restricting its domain to some curve. In this particular case, I'm restricting its domain to just the outer edge of the upper half of the circle. Do y'all see that? If I take just the points on that circle and just map just those points up into the curve, I get that blue curve on top. We've done something like this before, right? What we asked previously was what, though? If you restrict it and you look at that blue thing, what's what? The maximum, where the maximum minimums of that curve are, right? The highest and lowest points. That's what we asked before. Here's what we're going to ask this time. If we take that and we drop the curtain from the top of that curve down to the ground, then you create that wall, I guess, right? You create that wall there, and that curtain has an area to it, doesn't it? And we want to know the area of that. Or we would like to, right? So back in Cal 2, when we first learned about the integral, we actually didn't realize it at that time, but we were doing a problem just like what we're doing now, except our function was only a function of one variable, which means we didn't have a y component, did we? Like the y-axis didn't exist. And so, y'all see what I'm saying? Like we had x and we had z, but we called z y. Following that? And then our curve that we were restricting it to was a straight line segment. Thus, line integrals, we were restricting to a line. And so if you take this picture and you turn it sideways, you get back to Cal 2, don't you? But now we can look at it more in three-dimensional space. The main difference, we were integrating over a straight line in Cal 2. Here we're integrating over a curved path. And we've done the Riemann sum so many times, you probably are sick of me talking about it, right? But when we said area under curve, we did approximation with rectangle, right? And this right here on the bottom was dx, right? This was the function's height, f of x. So f of x dx was area. Integrate that adds them all up. Yes? Okay. The formula for calculus 2, finding this area, that's what I'm just saying here. dx was representing the width. We will have a similar result from our new problem. We first need a parametric equations to represent the curve. So remember curves, right? Curves, parametric equations, vector functions had parametric equations. You can draw curves with parametric equations. We need to figure out a way to draw that curve on the ground with parametric equations so that we'll be able to integrate this. And what we'll have to do is we'll have to figure out if we can express x and y, both x and y in the problem, as functions of t, like a stopwatch, okay, in the background, and then have some restrictions on that t between a and b. If we can do that, then what we have is this. We have the curtain, right? One rectangle in that curtain, notice if I look at it from the top, right? One rectangle, the width of it, okay? The width, how wide that is not dx. It's actually, this is the curve on the ground. Isn't the width of that rectangle approximately that piece right there? Which is an arc length, isn't it? This is a little arc length instead. And we have formulas for arc lengths, don't we? So this is what that line integral turns out to be. It is, look at the way we write this. It's a single integral, not double integral. It's a single integral over c. C is a curve, all right, of some function, f of x, y, ds. ds. It's the first time we've seen this, right? Well, since Cal 2 maybe. ds is equal to this, f of x of t, y of t. So what's happening here is, remember I said we're gonna find x in terms of t, y in terms of t, so we're gonna find parametric equations. We're gonna have to replace our x's and y's with those new parametric equations. And then this ds is going to turn into the square root of dx dt squared plus dy dt squared dt. That right there is the formula for arc length from Cal 2. If you're trying to find the arc length of a curve, that was it. And all this crap wasn't here. That's surface area, maybe. That's what you're thinking? If it was like, if you wanted surface area, you had like a 2 pi. Oh, 1 plus, that's if it was if y was a function of x only. This is called the line integral. This is called the line integral with respect to arc length, since ds in the problem is arc length. Please pull out the formulas I just gave you. Line integral of f along c with respect to arc length. There's your very first formula on this page. They go in order. I don't know if they match the notes, to tell you the truth. I don't. I think they do, but I can't promise that. So let's see if we can actually get our head around this with the problem, all right? A lot of times you work a problem out and it'll all start making sense, I think. So let's say we're trying to find the line integral of 2 plus x squared y ds, where c is the upper half of the unit circle, right? Quadrant, that means it's in quadrant 1 and 2. Is that good enough if I just say that? Or, you know, even better, I'll say y is greater than or equal to 0. Okay, what I'm going to do is I'm going to start with the region on the ground. Now, I shouldn't say region. I should scratch that. It's not a region, it's what? It's a curve on the ground, right? It's a curve. So let me start by drawing the curve on the ground. Oh man. Well, it's my attempt at this. Now what I need to do is I need to come up with a way of representing that curve where x and y are both functions of t. So in other words, in order for me to know what x is, someone gives me a t. Whatever y is, someone gives me a t. So what can I use? We've used things like this before. R cosine t would be x, but what's r if we're on this curve? 1. So we don't need the r, do we? We could just say cosine t. Do you all agree cosine t would get part of it going here? What would the y need to be? Sine t. And then if you're going to do that and you want to draw that curve, you better put a restriction on t or else you're going to draw the whole circle. So what do I need to restrict t to? 0 to pi? Does everyone see what I've done? I've come up with parametric equations for that circle, for that semicircle. Within those restrictions, I draw that curve. Now, I'm going to need to be able to compute this. Well, the notes are here, so let me just bring those up. I need to be able to compute the function that I'm trying to evaluate. I need to replace all my x's with that parametric equation for x, all my y's with that parametric equation for x. Then I need to do this arc length thing out here. So let me work on the arc length thing now, and I'll come back and I'll plug it in. How about that? Okay, so let me work on that. If I'm going to work on the arc length, don't you agree I'm going to need to know what dx dt is? Right? Well, what's dx dt? Take the derivative of x with respect to t, and you get negative sine t. What is dy dt? Cosine t. Now what I'm going to do is I'm going to try and write down what ds is. ds is equal to the square root of dx dt squared. Negative sine t, then squared, plus dy dt squared, cosine t squared, and then dt, which is just 1. which is just dt. It won't always be that nice, but you know, this is example. This is the first example. So understand? So now I'm ready to rewrite this integral. Yeah, right. When I rewrite the integral, going back to the formula, look what happens here. I go from the integral over a curve to integral from a to b. What's a to b? Those are my restrictions on t, right? 0 to pi. Now the function 2 plus, but instead of x squared, I have cosine t squared or cosine squared t. And instead of y, I have sine t. And then ds is actually going to turn into what? dt. And now we're just back to like a regular old Cal 2 integral. So what's the antiderivative of 2 with respect to t? 2t. Antiderivative of cosine squared t sine t is negative 1/3 cosine cubed t. So you have to just use a basic substitution. U is cosine t, and then figure out the signs and get that. And then you evaluate that 0 to pi. So if I plug in pi here, what do I get? 2 pi. What is cosine of pi? -1, right? Cubed, still -1, times -3, so plus 1/3. Now plug in 0. Plug in 0 here, it's gone. 0 here, cosine of 0 is 1, and I have then -1/3, but I'm subtracting -1/3. So you should get 2 pi plus 2/3. What does that answer represent? The area of that curtain, right? And actually, the way I worked this out, if I'm not mistaken, I believe that the area that we just found is that area right there. So this picture that I made here, this right here, is the problem we just did. So that green area is 2 pi plus 2/3. What do y'all think? Yeah? Okay, next note. If C, which is our curve, is the union of a finite number of smooth curves. Now, smooth, does anyone remember what smooth meant? Doesn't have bumps. When we talk about parametric curves or vector functions. Huh? Okay, well, let's not worry about it. For now, let's just talk about smooth as being, you know, no weird jagged corners or anything like that. If we've got a bunch of, if C, our curve, can be looked at as a union, that means grouped together, of a finite number of smooth curves, C1, C2, all the way to Cn, then if you want to know the line integral over the entire C, you can split it up into the finite sum of n integrals C over C1, C2, C all the way to Cn. That didn't space out too well, did it? That Cn kind of belongs further over here. Oops. Right? Makes sense? It's like you add the area of each curtain together as you move along the curve. So find, in this example, find the line integral over C of 2x ds, where C1 is the parabola y equals x squared from 0, 0 to 1, 1, and C2 is the line segment from 1, 1 to 1, 2. So I have it here. You can kind of see it. Maybe I need to spin it. Here we go. Whoa. So that's my parabola, and then I have a line segment. So the red is the ground, right? And 2x is a plane, isn't it? Which is why that blue thing looks like a plane. And so if we map that up here, we should get that. And what we're going to do is we're just going to basically take both curtains at the same time, do them each separately, and then add up those two areas, and then we're done, right? That's geometrically, that's what's happening. So let's set it up and knock this one out. We have integral over c 2x ds. C1 is the parabola y equals x squared from 0, 0 to 1, 1. And then C2 is the line segment from 1, 1 to 1, 2. Has anyone caught on to what the hardest part of these problems is? The arc length might be. Finding the parametric equations for the curves that you're trying to integrate over, right? That's the hardest part. I mean, the C1, C2, the whole idea of setting it up isn't so bad. The formula is not so bad. It's finding the parametric equations for x and y. So let's start with C1, okay? Let's take a look at C1. C1 is the parabola that starts out at 0, 0 and ends at 1, 1. I need a way of writing that parabola where x is some function of t and y is some function of t. And then I need to come over here and put some restrictions on t, right? I need like an a and a b. Now c, remember, comes from y equals x squared. Any suggestions? I had told y'all before when we were first doing parametric stuff that everyone could use their calculator and put it in parametric mode and do all the graphing that you've always ever done using parametric mode if you just replaced your x with what? No. T. If you look, if you have an equation solved for y like this, y is some function of x, all you have to do is say, let x be equal to t. All right? I'm going to put it here. If x is t, then what is y? Well, y is x squared, so y should be what? T squared. And then t should vary between where and where? Well, t is x, right? So what should it vary between? 0 and 1. And just check it for yourself. If t is 0, where are we? 0, 0. If t is 1, where are we? 1, 1. What if t is 1/2? Where are we? 1/2, 1/4. Which is, I mean, we're drawing the parabola, aren't we? With that parametric equation. Those parametric equations. That make sense? Okay, so let's try and set up the integral. We'll do the integral in a little while. We still need to set up the ds, don't we? Let's get ds. So for ds, I'm going to need derivative of x with respect to t, derivative of y with respect to t. What's the derivative of x with respect to t? 1. What's the derivative of y with respect to t? 2t. So therefore, ds will be equal to square root of dx dt squared, which is 1, plus dy dt squared, 4t squared, dt. Any questions? Here I go. The integral the line integral over C1 only, right? C1 only of, what was it, 2x ds should be the integral from where to where? 0 to 1 of 2, what's x for us in this problem? T. 2t, then square root 1 plus 4t squared dt. Yeah, this is a nice one. That's just a u sub right there. Right? If you let u be equal to everything under here, what's the derivative of that? 8t, and you have a 2t out front, so it's just off by a scalar. I computed this, so let me tell you what that would turn out to be. If you finish that one off, which I won't, you should get 5 root 5 minus 1 over 6. A numeric answer there. Is that all right? Now, we've only done over C1, right? Now let's do C2. Questions, though? Over C2, I'm going from, let's see, it's a line segment, right? It goes from 1, 1 to 1, 2. So 1, 1 to 1, 2. You know what? 1, 1 to 1, 2 seems boring, but we'll do it, okay. 1, 1 to 1, 2, right? I just want that line segment that goes from here to here. Right? Let me remind you how to come up with parametric equations for a line segment. It came from the idea of a vector equation of a line. Remember how we found the vector equation of a line? What do you need to find the vector equation of a line? A point and a direction vector, right? That point was really a vector, but it was, the idea was a point and then a direction. So don't I have a point and a direction vector here? If this is the point 1, 1, and this is the point 1, 2, then I can define the line, the entire line that goes through both, right? Goes up and down forever, by this, plus t, and then v, we use that as the direction vector. So what is a point on this line? Now, because I want to go from 1, 1 to the other point 1, 2, my initial vector, my initial point here, should be the one I start at, 1, 1. That's important. You, like, if this were just find the vector equation of the line between 2 points, fine. You just use either one. But because I want to go from 1, 1 to 1, 2, that just sounds weird. That I'm going to choose the 1, 1 as my initial point. Now, what goes in the vector right after t? 0, 1. That was the vector that goes from 1, 1 to the other point 1, 2. So you subtract the components, and you get 1 minus 1 that gives you the 0. Then you do the 2 minus 1, and that gives you 1. Right? You remember all that? And the key to doing it this way is that if you let t go between what two numbers, it will draw that segment. 0 to 1. That's the way it will always work. If you did it the way I just said, which means you have to use 1, 1 here, there, and then do the vector that you get when you subtract the point you're going to, or the point you're coming from. When you create the vector, your direction vector is the vector that goes from your initial point to your ending point. If that's your vector, not the other way around, then 0 to 1 will always work. Why? Well, if t is 0, this whole thing's gone, right? And you're at 1, 1, which is there. And if t is 1, then you basically add these two vectors together, you get 1, 2, and so you're up here. And if t is any number in between, it's just basically going to move you up this line, up that line segment. Now, that's the vector equation, isn't it? How do we go from vector equation to parametric equation? Well, first we have to do this. Combine these together. Do you agree with that? I just put this 0 and t is gone, so I just have a 1. And then 1 plus, and then distribute the t through, you get t. And isn't this the x component, and this is the y component? And therefore, those are my parametric equations. I have that x of t is 1, and y of t is 1 plus t. And t is between 0 and 1. That's the beginning. That's the first thing we need for C2. What else do we need to continue this? dx dt, dy dt. So what's dx dt? 0. Nice. What's dy dt? 1. Nice. What's ds then? Square root of 1 dt. So it's just dt, isn't it? Pardon? Yes. If your ds is 0. Yeah. Yeah, but think about it. Think about it. If your x, really the only way that's going to happen, right, is if one of these, if both of these are constant. But if both of them are constant, then you're integrating over a point. And so the area would be 0, wouldn't it? Right? If I say integrate over x is 2 and y is 3, well, you're integrating over a point, so you wouldn't have area. So it makes sense at least. Interesting. All right, now let's rewrite this. Integral over C2 of 2x ds equals integral from 0 to 1. It will not always be 0 to 1, right? I mean, it was 0 to pi in the first one we did, so don't get used to always plugging that in. And then 2 times what? Which is just 1, so 2, right? And then ds, which is just dt, 1 dt. And the antiderivative of 2 is 2t, and you evaluate from 0 to 1, so you just get 2. So take that answer, add it to the answer before, and you're done. A little bit, right? A little bit. Yeah, there's a lot of this parametric now, line segments, and yeah, it's not brand new. Not yet. Just Yeah, I guess we have to end it. In graduate school, the fire alarm went off one time when I was in grad school, and the professor's like, we're staying here. Well, hold on. Before we go out there, let's make sure there's no one out there shooting up the building or anything like that. Let me turn off this.